At first glance, stopping a train might seem like a simple task. Apply the brakes, reduce speed, and eventually come to a halt. But when you consider the reality, a machine weighing thousands of tons, moving at high speeds, often across long distances, the idea of stopping it becomes far more complex. Unlike cars, trains don't rely on friction between rubber and asphalt. They operate on steel wheels and steel rails, a combination that offers far less grip. And yet trains stop with remarkable precision, smoothly, safely, and in complete control, even under extreme conditions. So how is this possible? How do you slow down and stop something so massive without losing control? The answer lies in one of the most ingenious systems ever developed in engineering, a system that doesn't just apply force, but distributes it intelligently across an entire train. Because in railway systems, braking is not just about stopping, it is about coordination, timing, and physics working in perfect balance. To understand how train brakes really work, we need to look beyond what happens at the wheels. If you enjoy engineering explained in a clear and realistic way, leave a like, subscribe to RailTech World, activate the notification bell, and share your thoughts in the comments. Your support helps us continue exploring the hidden systems behind modern infrastructure. Stopping a train is fundamentally different from stopping a car. In a car, braking force is applied directly to each wheel. The system is compact, immediate, and localized. But a train can stretch for hundreds of meters, or even kilometers, with dozens, or even hundreds of wagons connected together. This creates a major challenge. How do you apply braking force evenly across such a long system, without causing instability, without creating dangerous compressions between cars, and without losing control? The answer begins with the air brake system, a technology first developed in the 19th century and still used today in modern railways. At its core, the system uses compressed air, stored in reservoirs along the entire train. A continuous pipe, called the brake pipe, runs from the locomotive to the last wagon. Under normal conditions, this pipe is kept pressurized. But here's the key idea. Braking happens when pressure is reduced, not increased. When the driver initiates braking, the system releases air from the brake pipe. This drop in pressure is detected by valves in each wagon, which then activate the brakes locally, almost simultaneously, across the entire train. This design is not accidental. It is fail-safe by nature. If the system loses pressure for any reason, even due to a failure or separation, the brakes are automatically applied. One of the most critical aspects of train braking is distribution. If braking force were applied only at the front, the rear wagons would continue moving forward, compressing the entire train. This could lead to derailments or structural damage. Instead, each wagon contributes to the braking process, creating a balanced deceleration from front to back. This transforms the train into a coordinated system, where every part participates in slowing down. Just like traction, braking ultimately depends on the interaction between wheel and rail. Brake systems apply force to the wheels, either through brake pads pressing against the wheel surface, or through disc brakes mounted on the axle. This creates resistance to rotation, slowing the wheel, and therefore the train. But there is a limit. Too much braking force can cause wheels to lock, leading to sliding instead of controlled rolling, which reduces braking efficiency and increases wear. To prevent wheel lock, modern trains use controlled braking systems. These systems regulate how much force is applied, ensuring that wheels continue to rotate, while still generating maximum braking force. This is similar in concept to ABS systems in cars, but adapted to the scale and complexity of trains. Sensors monitor wheel speed continuously, detecting any signs of slipping or sliding. If detected, the system adjusts braking pressure instantly, maintaining optimal performance. In many modern locomotives, braking is not limited to mechanical systems. There is also dynamic braking. Instead of using friction, The train's electric motors are used to resist motion. When activated, these motors act as generators, converting kinetic energy into electrical energy. This creates resistance that slows the train. In some systems, this energy is dissipated as heat. In others, it is returned to the power grid, improving overall efficiency. Dynamic braking reduces wear on mechanical components and provides additional control, especially at higher speeds, in critical situations. Trains can activate emergency braking. This rapidly reduces brake pipe pressure, applying maximum braking force across all wagons, almost instantly. The result is a much faster deceleration, but also higher mechanical stress. This is why emergency braking is used only when necessary, because while it increases stopping power, it also increases wear and forces within the train structure. Braking becomes more complex under difficult conditions. Rain, snow, or contamination on the rails can reduce adhesion, making it harder to slow down effectively. In these cases, systems must carefully adjust braking force to avoid wheel slip. Some trains also use sanding systems, applying sand to improve contact between wheel and rail, ensuring consistent braking performance, even in low adhesion conditions. One often overlooked factor is time delay. When braking is initiated, the pressure reduction travels along the brake pipe, but not instantly. This creates a propagation effect, where wagons further back respond slightly later. Engineers must account for this delay, especially in long freight trains, because uneven braking timing can create internal forces that must be carefully managed. In high-speed rail systems, braking precision becomes even more critical. Trains must decelerate smoothly, without causing discomfort or instability. This requires a combination of systems: dynamic braking, regenerative braking, and finely controlled mechanical braking, all working together to deliver safe and predictable stopping performance. Railway braking systems are designed with redundancy. Multiple systems operate simultaneously. If one fails, others continue to function, ensuring safety is never compromised. The fail-safe nature of air brakes remains one of the most important features, because loss of control automatically leads to braking, not acceleration. Braking generates enormous amounts of heat, especially in long descents or high-speed operations. Brake components are made from materials designed to withstand extreme temperatures. Heat dissipation is critical to prevent brake fade or damage. This is why braking is often distributed between mechanical and dynamic systems, reducing thermal stress at first glance. Stopping a train may seem like a simple action, but in reality, it is a highly coordinated process involving physics, engineering, and precise system control. From compressed air systems to advanced electronic monitoring, every component plays a role in bringing thousands of tons to a controlled stop. Because in railway systems, braking is not just about slowing down, it is about maintaining stability, ensuring safety, and controlling motion with absolute precision across every meter of the train.